Hello everyone and welcome back. Geometric series. So remember, this geometric series represent what? The sum of all the terms in a geometric sequence. So basically, this series here represent what? The sum of all the terms in a geometric sequence. And now, the sum of all the terms in a geometric sequence is actually given by this formula. Let's say is Sn is equals to A into 1 minus R all to the power of n, all divided by 1 minus R. So, but then there is a condition here. So if you remember, mathematically speaking, if you have your denominator as 0, therefore your equation will be undefined, or the value of this fraction will be undefined. That means the sum of Sn will not exist, it will be undefined. Therefore, in that regards, we will say now we don't want this thing at the bottom to be equals to what? To be equals to 0. Then you will say what? 1 minus R cannot be equals to 0. And then when you simplify it further, it will say what? R, when you transpose this one to the other side, it's going to be what? R cannot be equals to 1. So basically on a geometric sequence, there's this condition, and it's very much important because if your R is equals to 1, therefore that means your sum of all the terms in your geometric sequence is not applicable. Therefore, every time when you write this sequence, you must pay in mind this condition to say now our R can never be equals to 1. So now they might ask you in an exam to prove where this equation of sum of geometric sequences is coming from. So now I'm just going to show you how to prove the sum of geometric sequences, of which is a geometric series. So now here is a proof. So remember, in a geometric sequence, when you have your first term as A, to get to the next term, you must multiply by what? By a constant ratio. That means for us to get to the next term, we'll have to multiply by a constant ratio. Therefore, it will be A multiplied by constant ratio, which is R. Then when you move forward like that, you will also have to say now AR multiplied by R, which is what? Which is the constant ratio. Then you will get your answer being what? Being AR squared. Therefore, you will have to move forward, moving forward up until the last term of your geometric sequence. But now remember, the last term of a geometric sequence is actually represented by this formula, which says A multiplied by R to the power of n minus 1. No? So I will be correct to say now, in place of Tn, I can put A multiplied by R all to the power of n minus 1. So let me just put this one here in place of Tn. I'm just going to erase it here. And then remove Tn, and then put what? In place of Tn, which means the last term, it will be what? It will be A R all to the power of n minus 1. So remember, like we did in the previous video on proving arithmetic sequence, we also want to have at least 2 terms at the back of this last term. So now what we'll have to do is that because when we were moving forward, we had to multiply by the constant ratio to get to the next term. That means when we move backwards, we'll have to do what? To divide by a constant ratio to get to what? To the previous term. So now let me just erase this one here to say now if our last term is actually a all to the power of n minus 1, the previous term here, it will be how much? It will be a. When we divide by a constant ratio, we'll have a to the power of what? Multiply by r all to the power of n. Because remember, it will be r to the power of n minus 1 all divided by what? By r to the power of n by r, by dividing by r. So it's gonna be what? It's gonna be minus 2, because remember, when you divide the same base, you subtract the exponent. Let me just write it at the bottom here for you to say now when you have a r to the power of n minus 1 divided by what? Divided by r, which is the constant ratio. So now when you multiply the same base here, what do? You subtract the, when you multiply you add, but now when you divide you have to subtract the exponent. Therefore now we'll have a, and then the same base, which is r, we keep the base the same, and it's going to be n minus 1 because we are dividing. So basically we'll end up with what? With this negative 2 here. Okay, and then when we move backwards, you see now we're going to end up with this very same thing, but then the r will be r to the power of n minus 3, moving backwards like that. So now this is what? This is the sum of all the terms in a geometric sequence. And then when you prove, you must actually do this. You must multiply now. Remember, previously we had to rewrite the sum on an arithmetic sequence. You had to write it in a reverse way. But now in a geometric sequence, we have to multiply the sum of this arithmetic sequence by what? By r, which is what? Which is the constant ratio. So now we'll say, okay, we say r multiplied by Sn. So basically we say every term here in the sequence will multiply it by r. So a multiplied by r will have ar here. And then here ar multiplied by r is going to be ar squared. And then also here is going to be ar cubed. And then plus when we move forward like that, now remember we are multiplying by r. So now when you multiply the same base, you do what? You add the exponent. So basically we're going to have r all to the power of n minus 1. Let me show you where does this minus 1 come from again. So now let's say now we have what? We have this one here, which is r to the power of n minus 2, and then we multiply it by what? By r, because remember on the sum we multiplied everything by r. So we're basically going to say what? R to the power of n minus 2 multiplied by r. So remember now, when you multiply the same base, you do what? You keep the base the same, and then you add the exponent. So now we're still going to be left with a here, and then the r will be here, and then it's going to be n minus 2 plus 1. Remember now, you are multiplying, you are not subtracting. You subtract when you divide. So now when we are multiplying, we add. So our answer will be what? Will be a to the power r multiplied by n to the power of what? Of minus 1. Okay, I hope you understand. And then now we do the same thing moving forward. We multiply this last term of ours. So when we multiply the last term, we're going to have what? We're going to have a r all to the power of n. Remember, we'll have to do what? We'll have to add 1 here, because when you multiply by r, the same base, you add the exponent. When you add that 1, it will cancel out with this one, and then this is what you'll be left with. So now when you are at this stage, you will basically have to subtract, but now I just want to rearrange them to write them in a good way. I will first write this one here. Okay, our RS, our RSN is actually at the right position here, but now I'm just gonna rewrite this one here, move it here at the top, and write it at the bottom of R multiplied by Sn. So I'm just gonna say now, okay, let me just erase here to make a space here. So remember, we have R multiplied by Sn being equals to everything like this. And then now we just take this Sn here, just take this Sn just to put it down here. Just want it to make sense to you. And now let's just ignore it there. We are just taking it and writing it down here. So it's going to be what? It's going to be Sn is equals to, the first term is how much? The first term is A. Then it's going to be plus AR. Then it's going to be plus AR squared. When you move there, you're going to have what? AR cubed plus moving forward. Moving forward, you see we have this here. So it's going to be this. Okay, this part actually is also included here. I'm just gonna ignore it and then just write this part here. So let's say we have what? We have A R N minus 1, which is our last term. So basically what I'm saying is that even if I move backwards here, if I move backwards, I will also be left with what? With A. If I multiply or divide by R here, I will be left with what? With A R to the power of n minus 2. So basically I'm just omitting this one here. I'm just omitting this one here so that I can have the same number of terms in this R multiplied by Sn and also on Sn. So basically when you have arranged it like this, you just have to subtract. So now you will have to say what? You will have to say R Sn subtract by what? By Sn. So when you subtract here, you see it's gonna be 0 subtract A, of which is gonna be what? 0 subtract A, this is gonna be what? Negative A. And then now this one will cancel this one. This one will also cancel this one. This one will cancel this one. This one will cancel. This one will cancel out. And then here we'll be left with what? With A R to the power of n. So we can take the common factor on both sides, which is Sn here, and then here this side is what? The common factor will be A. So basically, when you take out the common factor as Sn, it will be Sn, and then we'll be left with what? With R minus 1. And then also at this side, when you take out the common factor as A, it will be A. Now when you take out the common factor of A, it's going to be negative 1 plus Rn. We can just write it as what? As Rn minus 1, which is the same as negative 1 plus Rn. So you divide both sides by R minus 1, divide both sides by R minus 1, so that you can be left with Sn. Then when you divide both sides, your Sn will be equals to this here. Okay, so you can also do what? You can also just multiply by both sides by negative 1 over negative 1, so that it can be in the correct format that I gave it to you on the previous slide. When you multiply by negative 1, you're going to have A into bracket. This will just interchange the sign, because when you multiply by negative 1, it just changes the sign. It's going to be what? It's going to be positive 1 minus R to the power of n. The same thing happens at the bottom. So it's going to be 1 minus R. Okay, so now this is what? This will be the sum of what? Of the geometric sequence, sum of all the terms in a geometric sequence. So let me just erase here because we have proven this. Okay. After we prove this, remember now you must also put in the condition to say now your R cannot be equals to 1. I have already explained why is that. Okay, let me just write it here at the top to say now our Sn is equals to A into 1 minus R to the power of n, all divided by 1 minus R. But there's a condition to say now the R cannot be equals to 1. The ratio cannot be equals to 1. Okay, and then you will get your marks for proving this equation. So now you must be aware now there's actually two things. So if ever now you have a sequence, let me just say for example a decreasing sequence like this. Let's say now you have a geometric sequence to say is 1 and then it's 1 over 2, the constants ratio, that means it will be 1 over 2. Then you divide there by 1 over 2, you have 1 over 4, plus moving forward up until to the last term. So basically, in this case, when you increase or when you move towards infinity of the number of patterns, basically your sum, your Sn will be approaching a specific number. It will be approaching a specific number. Let's say for example your sum will be 2, and then it will never get to 2, but it will approach 2, or yeah, it will be 2 or it will approach 2, or maybe it's a certain number. I'm not sure about that, if this 2 here is the right number to put here, but I just want to give you a little bit of an explanation here. So let's say now when you add here, you see now this is going to be 1 in your pattern, is going to be 1, and then you will add what 1 over 2 is going to be what is 0.5, and then now when you add here 1 over 4, let me just put on the calculator. I'm not good with mathematics, so I actually rely on my calculator. So basically 1 over 4 will be equals to what? It will be 0.25. So when you move to the fourth term here, when you divide by half again, it's going to be what? It's going to be 1 over 8. And then let's see 1 over 8. How much is 1 over 8? 1 over 8, it will be what? It will be 0.125. So as you can see now in this series of hours, when we move forward, as the value of n increases, basically what? The Sn is approaching a specific number. That means there's a decrease in number. There's a decrease in the value of actually there's a decrease in the value of the terms moving forward like that. But now this n is approaching infinity, because as it goes forward, the number of the position of the term it increases. But as it increases, every time the term is actually decreasing, is approaching 0, to say that. Now let's say we put all these few terms here in a calculator. Let me just put them in a calculator. When you plot all these values on a calculator, let's say 1 plus 0.5 plus 0.25 plus 0.125, our answer is actually 1.875. So what you will realize is that as we move close to n up to infinity, the value of what? The value of Sn. The value of Sn is actually approaching 2. The value of Sn is approaching 2. It will never get to 2, but it will approach 2. So it is not equals to 2, but it's actually approaching 2. It's actually approaching 2. So now in this case, we will say now, okay, now our series, our geometric series, it does what? It converges. It converges. So this is the term, when it does this, actually, the arithmetic series is what? It converges. Converges. So our geometric series, actually geometric series, it actually converges when what? When n is up, when n is going to infinity, the Sn will be approaching a specific number. Let's say in this case is 2. It will approach a specific number as what? As the number of terms increases. Yeah? And then there's another condition of, let me just erase here, of where we call that diverges, when the geometric sequence diverges. It's actually when now as the number of terms increases, now the sum of all the terms will also increase up to infinity. So now if this is the case, now what we will say? We will say now, okay, now the what? This the geometric sequence, it does what? It diverges. It diverges. Diverges. Yeah. So this is the terminology that they use to represent these two conditions here. To say now, as what? Sn increases, but then the sum of Sn is approaching towards a small number, then the series converges. But now as the value of n increases, and then the sum is also increasing towards a very big number, then the sequence is what? It diverges. Okay. So now, let me just erase again. Sorry for that. Let me just erase. You already know the condition of diverging and converging. So now, they say now, there's this condition to say now, only when the geometric sequence, what? It converge, not diverge. Converges. Ne? To say now, it will do that when the value of what? When the value of r is what? Is greater than -1 or less than 1. When it's between -1 and 1. So basically when the geometric sequence is it having this condition, therefore it will what? It will converge. It converges. Ne? So now this equation of ours, which is Sn, it will actually change the form. To say now, okay, let me just put here to let me show you something. Let's say, for example, now now let's say now what? The value of n, like for example in a sequence, the number of terms, they are actually approaching infinity. And then we have this condition of a converging sequence. We will actually say now the value of Rn, the value of Rn will actually approach 0, or it will be 0. Okay, so basically this condition, it says that because we know now the value of r, it will be a decimal number, because it will be a value between what? Between 1 and -1. That means it will be a very small number. So if you raise a small numbers, to say for example, let's just say small numbers are, you raise it to infinity, it actually becomes a very small number. For example, let's say when you have 0.2 all raised to 100. So basically, if you put that into your calculator, you will get, let me see, all to the power of 100. Your answer is actually approaching 0. It's 1.11 multiplied by 10 to the power of negative 70. So your answer is actually approaching 0. This means it's 0, 0,0000000. Yeah. So that is why we'll basically say the value of Rn will be 0 as n approaches infinity. I don't know if this condition makes sense. If n approaches infinity, the value of what? Of Rn will be what? Will be 0. So now as what? If only the series converges and then n approaches infinity, then you will say what? You will say the sum of Sn approaching infinity of a converging series. Remember, it converges when what? When the ratio is between -1 and 1. It will have what? It will have the value of a, and then r to the power of n will be 0. And therefore, 1 minus r. Therefore, the equation of the sum of infinity of a converging series, it will reduce to be what? To be a, because it's a multiplied by 1. 1 minus 0 is a, all divided by 1 minus r. So this will be what? This will be a sum of what? Of an infinite numbers of a geometric sequence that converges. The condition to put now, to say now, the value of r should be what? Should be between -1 and 1. I hope everything that I've just said, it makes sense, but I can repeat the video. If it does not make sense, please just comment below to say, can you please clarify or maybe repeat this video in a with better explanation. So now let's look at the example here. To say now we have an example like this. They say the common ratio of a geometric sequence is positive. Okay. So the first thing they give us to say now, okay, the common ratio. Remember, every time when you have a geometric sequence, you actually have a constant ratio. Your common ratio is actually equal, greater than 0, is positive. Yeah? And then as the statement goes, they say now, the sum of the first 4 terms of the series is equals to 73.8. Now they say what? The sum of what? The sum of the first 4 terms of this geometric sequence is equals to what? Is equals to 73.8. And then moving forward to say now, the sum of infinity of the series is 125. Find the common ratio of the first term. Okay, the sum of infinity of the sequence is actually equals to what? 1, 2, 5. Okay, so remember, I already told you now to say this sum of infinities actually appears when what? When your sequence or your geometric sequence converges, and then it converges when what? When the value of r is between what? Is between 1 and -1. So if ever we get the value of r being greater than 1 or less than -1, therefore this condition will not be applicable. Yeah? So basically what you're gonna do, we're just gonna simplify these two equations and equate them. To say now, remember the sum of the series is what is represented by Sn, which is equals to what? A into 1 minus r to the power of n, all divided by 1 minus r. And also remember again, the sum of infinite sequence is equals to what? Is equals to a over 1 minus r. Don't forget the conditions to say now. The r cannot be equals to 1 here, but also here, the r, it must be between -1 and 1. So these conditions, the value of r, it must meet these conditions. and then it must also be what? Be a positive value. Okay, so now let's answer the question. To say now we substitute as Sn is equals to 4, we substitute this one here, it's going to be 73.8. Then what is the value of A? We don't know the value of A. And 1 minus, what is the value of N? They give us the value of N is equals to 4, all divided by 1 all over R. And we will also simplify again on this side. On this side again, we substitute now, say sum of infinity is equals to how much? Is equals to 125, which will be equals to A all over 1 minus R. So when we simplify here, we make A the subject of the formula so that we can substitute this A into this equation. This other side, let's just make A subject of the formula. This side is easier. Then you say A, when you cross multiply, it will be 125 multiplied by 1 minus R. And then now you substitute this in place of A on what? On this equation. So we'll be having what? We'll be having 73.8, which is equals to, in place of A here, okay, in place of A here, we'll put this value, which is how much? Which is 125 into 1 minus R, and then we multiply by 1 all over R to the power of 4, all divided by 1 minus R. Okay, so now this 1 minus R will cancel out here because at the top everything is a product. Let me just erase here because you're not gonna need this information anymore. Let's just erase here. Let's erase. We can erase even the condition, we already know them, or they are there on the statement. Let's just clean here so that we can solve this thing very nicely. Okay, so now after 1 over 1 minus R cancel out, therefore we will be left with what? With 73.8 being equals to what? Being equals to 125 into 1 minus R to the power of 4. Okay, that means I can also erase here. And then now when we solve for the value of R, we just divide both sides by what? By 125. Divide both sides by 125. Okay, let me just put this in the calculator. 73.8 divided by 125. Therefore we have 0. This is 0.5904, all being equals to 1 minus R to the power of 4. So now when we do what? We're just going to transpose this R to the power of 4 to be positive this side and then subtract this from that one. So basically we'll say R to the power of 4 is equals to what? Is equals to 1 minus 0.5904. Therefore R to the power of 4 will be equals to, let's say 1 minus answer, then it's going to be 0.4096. Then you apply what? The fourth root to cancel this thing here, the fourth root. Then remember, when you apply a square root that has a root that has an even number, that means your answer can either be positive or negative. It can either be positive or negative. So this will cancel out here, and then now the value of R will be 0 0.64. It's either negative or positive 0.64. But then remember the condition, they say that the value of R is what? Is positive. Therefore, the value of R, it will be how much? It will be 0.64. Okay, then in this case, therefore, the value of R is acceptable because it falls under the two conditions of what? Of a normal geometric sequence and also an infinite sequence. Thank you very much.